Good morning, everyone. Afternoon, close enough. It was a 50-50 shot, I guess. As Jess said, this is going to be about the system we have here put together here at the Space Science Center that does currently produce VIIRS, MODIS, and CrIS products within 60 seconds of satellite observation. Should I mess this up? So I just got to press the button. Okay. All right. Just a brief introduction. I'll give a short description of the system. I'll give you an idea of what type of participation we currently have in the system. We can talk a little bit about the types of applications a system like this might apply to. Time permitting, I'll go over some broad strokes of how the components of the system and how it is we accomplish the kind of latencies that we get, and talk a little bit about the kinds of challenges we run into trying to do this type of thing. And additionally, people have been talking a lot about latency here and there. I want to be clear about the terminology that I'm using for real-time and near-real-time to describe our latencies. When I talk about real-time with this particular system, I'm going to be referring to data that's processed as it is received, generally on the order of seconds of latency. And when I refer to near real-time, what I'm referring to is data that is handled after the overpass is over, generally via an ingest process or a push mechanism. That's generally speaking, that's on the order of minutes of latency. Oops, hit the wrong button. So generally speaking, this is the DBRTN ULL brochure. Kind of some general characteristics of the system. Like it's been previously stated, the goal of the system is to provide products within 60 seconds of satellite observation. Similar to, but distinct from the processing system that Liam just described, this is a centralized processing system, meaning that we have a network of participating direct broadcast receiving stations that all send us data. And at our centralized processing facility, we handle the ingest, archive, processing, and potentially the distribution of those products as well. But along the lines of what Liam had previously mentioned, this is advantageous because it is a common set of software lookup tables and hardware, giving you a better hold of the provenance of your system or the provenance of your products, and generating a more consistent product. And it does obviously provide you a reduced maintenance cost as well, because you're taking the bulk of the heavy lifting of your processing and you're moving that to a central facility that's closer to the people that maintain it, as opposed to potentially on the top of a mountain in Puerto Rico, where it would be hard to get to and hard to maintain. The system does currently have two modes of operation. We have a streaming mode, which aligns with like the definition I gave previously about the real time. And then we have a hybrid mode. In the hybrid mode, what we do is, in order to increase participation in the system and kind of lower that barrier of participation, we accept traditional near real-time data, which would be the granules that are produced after the overpass is received, and then via that ingest or push process, arrives here at the processing facility, where we extract the level 0 data, from an RDR if necessary, or just take that level 0 data as it's received, and then ingress that into the same system as the real-time streaming mode. It is simultaneous reception. If you have multiple receiving stations seeing an overpass at the same time, we do receive that data in real time, and that data is both merged and deduplicated to produce a best case set of level 0 as a single data stream. It maximizes your coverage. If Billy's over standing next to your antenna and he makes a 5G phone call and you get some dropouts over there, and another station is picking up that stream, that is all handled in the merge and deduplication process to give you a consistent stream of data. Additionally, there is some level of redundancy there. Obviously, if you can merge and deduplicate, if that station drops out completely, depending on what type of coverage you have in your stations, you could give yourself the opportunity to not have any data loss due to that simultaneous reception. This one's a little out of place, this bullet in particular, but I didn't really have another place to put it where it fit well, so I'm just going to jam that right in here. The processing we do is based on sensor scans. So when we're processing data, we don't operate on granules, we don't operate on big segments of data. This processing system operates with the intent of more or less producing as small a set of data as we can. And to this point, kind of as a restriction on the algorithms we currently have to work with, that's generally a sensor scan. It is a modern cloud-ready stack. When you talk about systems such as this, people always inevitably ask you, have you thought about the cloud? We have. We think we have a pretty portable architecture. It's based similar to Dave's talk previously on a Kubernetes cluster. We kind of treat our cluster as an application. That's the way in which we manage portability and avoid vendor lock-in between various different cloud providers. The entire infrastructure does run containerized. We also do containerize our science code. We do make use of the Singularity or Aptainer containers for that. It is a high availability system and a redundant system, such as provided by our Kubernetes orchestrated component. And we have built into the system and the various components of the system a lot of tools for monitoring and metrics to make sure that we're aware of the current performance of the system and if any issues. And then furthermore, out at the receiving station, it is minimally intrusive for participation. In the real-time preferred streaming case, it's a single binary that gets installed at the direct broadcast receiving station, low CPU usage, low memory footprint, and plays nicely, generally speaking, with the other software that may be running at the antenna, if that's important. There are 3 different modes that we can use to receive data from a direct broadcast station. I'll get into that a little bit later on why exactly that is. And the algorithms that we currently have integrated include the FIRE algorithms we got from NASA LANCE, including the VIIRS FIRE locations and the MODIS FIRE locations. And we do those for both SMPP, NOAA 20, and Aqua and Terra. And we are currently running the NASA CrIS Level 1 for both NPP and NOAA 20. Coverage-wise, I wish I could produce the prettier plots that some other folks do for their coverage, but this is what I have to work with. We currently have 9 receiving stations that are participating. We got a couple of stations here in Madison that are contributing MODIS, VIIRS, and CrIS. That's the MVC next to the station names. And Hampton and Puerto Rico are providing the bulk of our CONUS coverage in the real-time streaming case. And we are augmenting our coverage with the 5 near real-time stations listed below. Just tell me what the latency is. That's what everybody wants to know. How fast can we produce products? We don't have that boring regular latency. We have that ultra-low latency. You see the smile on her face? That's good. Well, this is how low ultra-low is, or as low as we can get it. Currently, with our real-time streaming stations, we're currently able to produce VIIRS FIRE products, FIRE locations within about 50 seconds of satellite observation, and about 30 for the MODIS FIRES. And we're currently able to produce the CrIS Level 1 products at just under 30 seconds. Down below, you see this is the full resolution, kind of like a dot for every processing job that we run. An interesting thing to note here is the vertical trend you see in some of this data. That's kind of interesting because that's due to resource contention. The system is currently running on shared resources. And as the system gets busy, our real time becomes a little less real time because that stuff starts backing up in the queues as the resources are freed up. So is the processing mechanism. And why that's important is because we have incoming hardware to have our own dedicated processing system for this low latency application. And I really suspect that these plots are going to flatten out quite a bit, thereby reducing the latency you see here even further. I almost didn't include this. I did because I think it's kind of cool. This is the near real-time case. It's hard to really quantify the latency on the near real-time case because it does include a variable length of time that is the satellite overpass. The important thing to see here is that in the graphs down below, you see that vertical structure again. And the reason you see a lot more of that here is because in the real-time case, you're only handling data at the data rate at which the satellite can provide it to you. And MPP's, 15 megabits a second. In this case, we download the entire granule, we do our extraction process, and then we fire that into our system as fast as we can. And that's the only thing you're limited to is your local network latency. So we're talking this data is feeding into the system at gigabits a second. And I mean, you'd have to have very, very wide resources to be able to keep up with that processing in this case. So it's still providing excellent latency though. Oops. What are some type of applications you might use for a system like this? I don't know. To be honest with you, I'm a software developer. If it sounds like I'm a little wishy-washy on the science, that's because that's absolutely true. From my point of view, Liam might be able to have a more interesting conversation at this level, but from my point of view, I'm just really interested in kind of pushing the limits of what the system can do. And I think we've shown that we can very reliably produce data with latencies that are very, very ultra low. I can tell you on the direct broadcast side of things, we are participating in a pilot project with VIIRS, NASA VIIRS, that's Fire Information Resource Management System, to produce low latency fires for them. And it's a bit of an interesting story. They came to us looking to integrate our direct broadcast products to potentially get data with latencies of 20 to 30 minutes, and we let them know about our low latency system. So they came in expecting 20 to 30 minutes, and they walked out the door getting 60 seconds. So I felt kind of good about that. I'm just going to name drop here on some other applications I heard just in some earlier presentations. I think Mike had talked about some volcanic ash is very latency sensitive, nowcasting, NWP. I don't know what that would look like, integrating data of this sort into that, but I got to imagine there's some sort of application there. An interesting one that I'm particularly interested in is, it's been kind of a thought experiment really so far, is what about global data? I mean, the global SMD data comes in for NOAA 20, you get an overpass at Svalbard and one at McMurdo with minimum latency. Well, what if you took that data and you could pipe that in? I mean, level 0 data is level 0 data. You could pipe that into our NRT mechanism, and with enough processing resources, you could really reduce that latency because we're processing in such small chunks of data. So it'd be interesting to think about what that might look like for latency for global NRT products. I'm kind of running a little short on time, but this is kind of the broad strokes of the way our architecture is put together. It is in the presentation if you'd like to check it out afterwards, and when the presentation's available, that's great. Or if you just want to come and ask me about it when we're done, I'm happy to talk about it. But I didn't want us to skip the chance to talk about some of the challenges that we ran into trying to put together a system like this. Most of them were due to the science software itself. We're kind of using the software in a way for which it was not intended to run. There's some basic assumptions the science software makes kind of on granulation and how much you have to process that can cause you to fight a little bit to get the software to run on the smaller chunks of data that you're producing. A lot of reverse engineering back and forth. Steve is a wizard at this stuff. Steve Dutcher, he's been able to figure out basically reverse engineer the software in such a way that we can figure out what's the smallest chunk of data we can process and still get something that compares well to the global data. There's also trade-offs that we had to make between latency and completeness. We use microgranules, as we call them, to process our data. That's approximately a 5-second chunk of data. At the level 0 level, it's really hard to know when that is complete. It seems like it would be straightforward, but it's not really that straightforward. So you end up setting timers and deadlines. Like I'm gonna wait for this data to be available for X number of seconds, and then I have everything I have, and we're just going to forward that data on and hope it's as complete as possible. So you got to kind of trade off between, you want to make sure you have all the data, but you don't want to add latency to the system unnecessarily. I think Russ had mentioned something about this previously. We don't currently have any use cases that require fan in. Like we take our data and we fan out and process it in little small chunks. We haven't currently created a mechanism to fan that back in to create a level 2 product that maybe you need to aggregate back into like more like an image type product. That could be a bit tricky to do. So we've been kind of banging around ideas on how to handle that. And additionally, there is some issues dealing with some older direct broadcast stations. Stations, in my experience, tend to get ignored and kind of left to dwindle. So you end up with some very old operating systems. Our stack is pretty modern, and it's really hard to get stuff to compile on some of the older infrastructures and stuff, so that's been a challenge as well. I don't have any particular elegant end to this talk, so I'll just say thanks for listening. I hope you got something out of it. If you have any questions on this stuff, feel free to grab me in the hall. I'm kind of geek out talking about this stuff. So.
Thank you, Bruce. Do we have questions for Bruce?
Thanks, Bruce. That was great. It's very impressive. You mentioned that most science algorithms operate on a granular because they're, every pixel is not necessarily independent in an algorithm, especially that's true with fire because it's contextual. Have you gotten any feedback from the NASA team about the impact of processing very, very small scan-line chunks and the impact that's had on their quality? It's obviously coming out fast, but is the science quality and usability, is that maintained when you're processing on these smaller chunks?
We have at this point done comparisons ourselves. We haven't talked to the algorithm developers themselves as of yet. I think Steve could probably comment a little better towards the comparisons. He's the one that kind of runs all that stuff for our team.
Yeah, so when we do the level 1 processing, we actually take, we've done a comparison between the geolocation between the standard system and products, and there's slight differences in the geolocation, but the L1D comes out identical. And we also are grabbing the firm's data, their fire locations, and comparing them to ours, and be like, hey, this is those failures, but we missed this one, and figuring out why. So it's pretty much at that point at this point.
Okay, I believe Liam had a question.
Extra pressure when the boss has a question.
Great presentation. Thanks, Bruce. So you mentioned the software that's used for level 1 processing, but you didn't say, is that CSPP? Is it something else? Where does that software come from?
Oh yeah, I'm sorry. We are currently using the NASA algorithms. I mean, I think I did mention the CrIS level 1 that we're running, but we are also running the NASA VIIRS level 1, currently version 3.1. And that's, I mean, not due to any specific preference. I mean, we don't think it's better, we don't think it's worse. It's really just a matter of flexibility and rigidity. We're more familiar with that software. We know how to play with that software more, and we know how to, it's just more predictable for us. On the CSPP side, that ADL chunk that it's based on can be a bit of a mystery. And we really, really don't like RDRs.